So calorimetry, and I've got a little bit of a description on what calorimetry is, and you can write that little definition down. The amount of energy that can be transferred into or out of a substance to facilitate a temperature change depends on 3 factors, but one is obviously mass, all right? If I have a tiny little amount of water, and I put that little amount of water out into the sun, it's going to heat up quite quickly because there's not a lot of water to heat up. That energy is going to cause those vibrations to happen very quickly, and it heats up very quickly. If I have a large swimming pool of water and it's out in the sun, it's going to take a lot more energy to get it to heat up to the same temperature because there's a lot more molecules to put the energy into. So the more matter you have, the more energy it can take in to heat up or give off to cool down, right? So mass is 1. The more mass you have, the more energy that it will take to heat it up. The second thing is something called the heat capacity, and that's a fundamental property of the matter itself. Water is very good at absorbing heat energy, right? The reason water is very good at absorbing heat energy is because it's got lots of bonds, not lots, but it's got 2, and it can vibrate, rotate, and translate. It can move all in these different ways. If I've got something like copper, copper is made up of just a bunch of copper atoms that are in a lattice structure. It's not able to move and rotate and translate. It doesn't have bonds that it can wiggle back and forth. The only thing the copper atoms can really do is shake back and forth, which means if I add some energy to it, it's going to shake back and forth quite quickly because all of the energy can go just into vibration. It heats up quick. Metals and copper, stuff like that, heat up quick because there's nowhere to store the energy. Something like water, you can store all kinds of energy in a water molecule. You can make it rotate, you can make it vibrate many different ways. It's able to suck that energy up. You can see here we've got some heat capacities. For water, it's 4.18 joules per gram degree Celsius. It will absorb 4.18 joules for each gram that it has and each degree Celsius that it moves up by 1. If I look at some metals, and I don't have copper, but iron is here, 0.44 joules. For each gram of iron and each degree Celsius it goes up, it can only absorb 0.44 joules, but water can absorb 4 joules. Water is 10 times better at storing and absorbing energy than iron is, or any metal. Aluminum can absorb a little more, but it's not great. Ice, not quite as good at storing energy as water, because again, it's locked into its crystal structure. It can't rotate and translate as easily. Methanol, that's a type of alcohol. It's still not as good as water. Water is a great heat absorber. Okay? So the specific heat capacity is given the letter C. It's a fundamental property of all materials, and it kind of describes how good it is at absorbing energy. And the last thing is the temperature change. If you have something absorb energy and it only changes by 2 degrees, then it's absorbed a little bit of energy, but if it changes by 4 degrees, it's absorbed twice as much energy. So the greater the temperature change, the greater the energy that's been absorbed. And we represent that by delta T, and I think we're all aware that a delta means final minus initial. We'll do some calculations on that. All I want you to write here is Q equals MC delta T. And I'm going to do this the good old-fashioned way like I used to do when I teach physics. I'm now going to just define these things with a nice arrow right there. That Q is the heat. That's the thermal energy transferred. That's how much energy either came in or went out, depending on the sign. And the units are joules. M is the mass of the substance. Its units, grams. If we were doing this in physics, which you may have done, you would have used kilograms maybe, and then a different C would have been moved over by 3 decimals. Chemists like grams. I don't know why. We don't like those great big masses. Kilograms, they're scary. So big. Drop it on your toe, it would hurt. C, the specific heat capacity. The word specific implies that it's for 1 gram of substance, all right? And I'm going to just put the units here, and that unit is joules per gram degree Celsius, with both the gram and degree Celsius on the bottom. You may come across questions, I hope I don't have any questions in my handouts, but in the future you will come across questions that just deal with the heat capacity, all right? Now don't write this down, but the heat capacity, which is a little different than the specific heat capacity, is if you combine the M and the C. If you combine the M and the C, chemists call that capital C, and they just call that the heat capacity. Don't write that down. But that's why I put it in yellow. I don't want you to actually write it. Don't worry about it. But sometimes scientists will just talk about the heat capacity of a substance. And what that simply means is, well, let's take the number of grams, right, the total mass, multiply it by that specific heat capacity, which is like kind of how much each gram can do, and then that's the overall heat capacity, all right? So that's a term you may encounter in the future. We're going to just deal with the specific heat capacity, and then I'll give you the mass, and you can then, what you're doing, you're figuring out the heat, the overall heat capacity. But that's the little things that you'll learn about in the future. Okay, so don't write that down. That's not important. It's just a term you may encounter. And here we've got the temperature change. The temperature change. All right. I've got a question in my worksheet that has Kelvin in it. Even though this says joules per gram per degree Celsius, a degree Celsius degree is exactly the same size as a Kelvin degree. So you don't have to convert Kelvin. You can just subtract Kelvin temperatures as well, and you'd still be able to get the same answer because it's just the difference. So if you get numbers in Kelvin, you can leave them in Kelvin. You can just subtract them. You'll still get the same answers. Temperature change, delta T. I'm a fan of T2 minus T1 instead of final minus initial. That's just my physics background. If you like final minus initial, that's fine with me. And it can be in degrees Celsius or Kelvin will work. So what we've done at this point is we've learned how to calculate how much energy the surroundings are gaining or losing. And that's good, because the next step will be to apply that back to the system. So we're now just looking at the surroundings that are in my coffee cup calorimeter here, the water here. We're just looking at that. We're just starting so that we can apply it next to the system. Let's do some example problems. Okay. Okay, there's the equation. No need to write that. We just did that thing. All right, there we've got some practice problems. And again, we're just copy and do them, you know, good old examples. In textbook questions, they tend to have a table nearby, very much like this, that they make you go and look up the heat capacity if you need it. So, determine the amount of energy. I'm looking for, well, determine the amount of energy required. In other words, that's a transfer of energy. That's a transfer of thermal energy. So what am I determining? Which of my variables am I solving for here? Yep, Q. So I'm looking for Q. Q equals MC delta T. And you know what? Again, writing down data is great, but we're grade 12 veterans. If we can just pluck the data out and put it in, that's great too. I'm all for plucking data out and putting it in. Mass, 25.0. Again, you know my views on units. Some professors will be picky about it. I'm not picky about it. I'm going to include it on this first one just so I can show you the way the unit analysis works. The C, what is it for? What are we dealing with? Water. What's my C? Yep. 4.18, 4.18, and that is joules per gram degree Celsius. And by the way, that C is the only one I'm going to make you memorize. because we're going to be dealing with water over and over and over again. That's what's going to be our surroundings, which means if I tell you a question that you've got a coffee cup calorimeter and it's got some water in it, I'm not going to tell you the sea of water. We're going to use that one so many times that I'm going to expect you to memorize. Delta T, and we can do this all in one shot. We've got to be very careful which is the second and which is the first. Starts at 25, goes to 75, so 75 minus 25. That's very important because if you switch it around, you get a different sign. And that sign is going to tell you whether the heat content went up or the heat content went down. And that's going to be very important in the near future. So, this has units degrees Celsius. The reason I put the units, this guy will cancel this guy. The grams will cancel the grams. And notice we are left with the unit joules. And I will take somebody's answer, and it's looking like 2 significant digits for the temperatures. That's what it's looking like. What do we got? Yep, right? 5,200 joules. Rounded to 2 significant digits. We like that? Supporters on that? I guess maybe to take the ambiguity away, 5.2 times 10 to the 3 joules. Right? That would be scientific notation. Or we could even do it better, times 10 to the 3. I don't have it on my wall anymore because I took them down. It's on your sheet. What prefix is 10 to the 3? Yep. Kilo. So we could say 5.2 kilojoules. That's also going to be something we're going to be doing a lot in this course, bouncing back and forth from joules to kilojoules. So that's a step that we want to practice. Okay. Positive means that the energy content of the water increased by that much. In other words, if we were to say the surroundings was a bank account, the water's bank account has gone up a little bit. It gained a little bit of heat energy. Okay? All right. Let's do another one. Now in this case, we're not dealing with water, we're dealing with iron. So this time now the iron is absorbing some energy here. They tell us the energy to increase the temperature, and we're looking for the mass. All right? So again, our equation, Q equals mc delta T, and this time I'm looking for the mass. I like rearranging first, but I know some people like to rearrange after, so we'll do the after. We've got to be very careful here, because what unit is my Q in this equation? It's in joules. Notice the energy unit they've given us, kilojoules. What's the easiest thing? How's the easiest way to convert that thing? Yeah, Jess? Yeah, times 10 to the 3. Just to stick a times 10 to the 3 on the back end. Joules. So the equation uses joules. If you're dealing with kilojoules, you gotta convert it over. We're looking for an M. C for iron, 0.444. Delta T. Again, I like putting it all in one shot. Again, we've got to be very careful. From 45.5 up to. So 85 is the second one. 85.7 minus 45.5. Remember, we got to do these brackets first, and then we'll divide off. And I don't want to mess up the slide here, but you know, I could divide by that subtraction. I don't have that. What is that? 40.2? Looks like 40.2. Anyway, got to divide off 40.2. Got to divide off the 0.44. M equals. Do we have a number? Jess, what do you got? 68.4. Looks like 3 significant digits all the way along. Grams. We like it? We like it? We don't like it? We do like it? 67.5. Didn't get the 67.5? No. It's looking like there's a lot of support for 68.4. Anyway, do we need multiple? Do we have a check on it? We like it? I don't know what's going on. All right. Questions, concerns? Okay. What are we looking for in this one? What are you trying to find? Yep. T2. Now, you know what? You could substitute it all in and have T2 in there, but that becomes a little tricky. You can easily do it, right? The mathematics isn't bad. But if you're not great at algebra, what I suggest you do, if you're looking for a T2, like in this case, I would solve for delta T. Solve for delta T. As soon as you know what the temperature change is, you can apply it to what that first temperature was and tell me what the final temperature is. So that's kind of a little bit of a trick. You could put in T2 minus 22 and rearrange and solve, but you could find the delta T and apply it to that. That works as well. Q equals MC delta T. And we've got 1.25 times 10 to the 3 joules. The mass is 50 grams. We've got aluminum, so we can check our table, 0.900, and delta T. And if we then divide off both of those, what do we get there for a delta T? Oh, hold on 1 second. We need to check a sign here, all right? What would the final temperature be if the 50-gram piece of aluminum had 1.25 times 10 to the 3 joules of heat transferred into? If the energy is going into it, what's the sign on this energy? What's the sign on the aluminum's energy bank account if energy is going into the aluminum? Yep. Negative. If you put money into your bank account, positive. Positive. Because energy is going into the aluminum, this is a positive energy transfer. We're putting energy into the aluminum. That means this is positive, and therefore my delta T will be positive, which makes sense. If you're going to put energy into the substance, its temperature is going to go up, a positive temperature change. And that implies energy has been added. So what do I get here for an answer? What do we got? Been babbling away here. Shauna, what do you got there? You were pushing the buttons on a calculator. It looked like you were doing something. Were you spelling little funny words, turning the calculator upside down? Yeah, that kills some time. Don't make me go to Jessica. Don't make me do it. What do you got, Ryan? 28. And actually, we got 3 significant digits going. 28.0? 27.8. We better keep our 3 significant digits. Let me get the eraser here. 27.8 degrees Celsius. Now that's the temperature change. So you could rearrange the equation, but if you think about it, if you start at 22 and the temperature change is plus 27, you're going to add those two things together. 22, it's 0.0 degrees Celsius. Look at that. That degree's in the wrong spot. Degrees Celsius. You get the idea. Plus 27 point, oh my God, that's an 8. Look at that. Is that supposed to be an 8? That's horrendous. What do I have here? 49.8? 49.8 degrees Celsius. Okay? All right? There's my number 4. Once we have this written down, I'll go to the Smart Notebook program and we'll do it on a white page like that. So this is a little different. Here we've got 2 samples of water. They're at 2 different temperatures, and we're mixing them together. So the hot one is going to give a little bit of its energy to the cold one, and the cold one's going to warm up a little bit, and they're going to get to some temperature that's the same in the middle. This is like putting 2 of our Q equals MC delta T equations together as one. So what do we have? We have a sample of water and a second sample of water, and I'm actually going to ask you for the data on this. If we call this sample 1, all right, actually, we use 1 and 2 for before and after, don't we? So I can't call it 1 and 2. So let's call this sample hot. We'll call this H. And what is the mass of the hot sample? What is the mass of the hot one? Sorry? 35 grams? 35.0 grams. And the C of the hot sample is what? 4.18. Excellent. Sorry? What? Did you say 4.18? No, you didn't, obviously. Well, we're dealing with water, right? So it's 4.18. We got 2 samples of water here, don't we? 2 samples of water? Okay. And a T2, all right, and a T1, and we know what the T1 is. What's the initial temperature of that water? The hot one. Yep. 325 Kelvin. And T2, well, that's what we want to find, right? We want to find that final temperature. We'll call this cold. What's the mass of the cold? I don't recall because it's not on the screen anymore. Sorry, 45 grams? 45.0 grams. The C of the cold is, it's water, isn't it? Now, in the questions on the page, it not necessarily it's water mixed with water, but it might be like a piece of iron put in water. So you might have 2 different C's. In this case, the C is the same because they're both water. 4.18. T2, unknown, T1. What's the T1 of the, sorry, 278? 278. Excellent. Kelvin. Now I do have to put a couple more marks here because I want to make sure I differentiate between my 1s and 2s. So this is like T2 hot and T1 hot and T2 cold and T1 cold. Okay? Well, essentially, the Q, right, of the hot, the amount of heat that is given up by the hot is going to be equal to the Q of the cold, the amount of heat that's given up, that is accepted by the cold. That's the law of conservation of energy, right there. It states that the Q, the heat that is lost by the hot one, is going to be gained by the cold one. Does that make sense? That means that the exact amount of heat that's lost is gained. Except there is one difference. If the hot one is losing energy and the cold one is gaining energy, I do have to add one more thing here. Yep? Yeah, the hot is going to be a negative sign because it's going to be losing energy. Make sense? So now we're ready to input our information. I'm going to extend the page here so that we can get a little further down. So negative, M hot, C hot, delta T hot, but I'm going to put here our T2. What's going to be true about both T2s? After we've done mixing them, and the hot one is cooled down, and the cool one is warmed up, what's going to be true about both of the T2s? Yep, they're going to be the same temperature. So I don't really need to say T2 hot and T2 cold because the T2s are equal. Let me just put that off to the side here as a statement. T2 hot equals T2 cold, and let's just call that T2. The same thing in our equations. So T2 minus, and then it's going to be T1 hot, that's different, and then it's going to be M, sorry, do you see what I've done here? I've put a cold, and those are supposed to all be hots. I apologize. Mass, cold, C, cold, T2 minus T1 cold. I haven't put these in past years. I've reintroduced it, so I haven't done these in a while, so I'm tripping over it as well myself. You grade 11 veteran physicists should be helping me here. Let's put our information in. Minus, and what was that mass? I can't move my screen up, can I? 35? 35.0. 4.18 T2 minus and 325. 325 mass cold. What was it, 45? 45, 4.18 T2 minus, what is that temperature? 278. Now we got to rearrange and isolate for T2, and we've got it. We've got to do some algebra here. But we can cancel out this 4.18 right here. So yeah, let's FOIL it through. This 45 is going to go there, which means I'm going to have 45.0 T2, and I need that number 278 multiplied by 45. If someone could give that to me, that'd be great. Someone going to share that with me? 45 times 278? No? All right. Yeah, what do you got?
12,500.
And on this side, you could bring the negative in. Sure you could. So it would be negative 35 T2, negative 35 T2. And then negative times negative would make it plus. So what's that 35 times 325? Yep. So let's gather up our T2s. I would bring the negative over here to make it positive, so we're dealing with positives, and I'd bring this guy over to the other side. So I'd have my 11,375, and that's going to be plus 12,510 equal to 45.0 T2 plus 35.0 T2. So I can put those two together, 35 plus 45, that's 70, that's 80. 80 T2. And how about this big number here? Somebody got that put together? Yep.
23,800.
And now we're dividing off 80. Divide off 80. Divide off 80. And T2 equals. Now this will be in Kelvin because we've been working in Kelvin. What do you got? 298.6 Kelvin. And we've been dealing with 3 significant digits, so we need to round that. 299 Kelvin equals T2. And obviously it is at some intermediate temperature, and it's actually probably going to be a little closer to the cool one because I believe we had more cool. We had a little more cool than warm. All right, so that's the most complicated version of it. All right, but that also uses that conservation of energy that when one loses, the other one gains. Okay? All right, so that's the end of today's lesson.